let's go back to the original machine learning problem, right? Like, so where typically you are provided with some data, let's just call it X, and your goal in machine learning is to come up with a model which fits the data well, right? Like, and we are not interested in just fitting the data. We are also interested in generalization. So it's like, it's not interesting if I have a model which has zero training error, but very bad generalization error, right? Like, so we want to fit the data with the goal of generalization. And whenever I say you fit the data, it typically means find the parameters of the model. Is done, right? And who gives us this data? Like in any problem, typically the data is generated by some natural process, right? Like, so if you're interested in coming up with a weather prediction system, like the data for you is all the historical records, and this data actually comes from nature, right? So we don't have control over this. And so typically the data is generated by a random process. Sometimes it's natural, sometimes it's artificial. Let's just call the process as del X. Okay, so del X is, yeah, yeah.
Say I want to train a model to recognize certain tones. So I'm going to use something like audio effects and then use like a random generated function for that level and set to audio file like different sound at different spaces. Is there a chance that if I use specific agents to learn this to build on my agent, like it's going to try to fit this random or really random generalization?
So is the question, can the model learn a random?
Yeah, it affects like the fact that it's not
Oh,
police.
no. Well, as long as the model has enough capacity, it could learn anything, right? Like, so this actually includes even purely random functions. Like, so you could have a random data set, and there are work which shows that larger powerful neural networks can just fit the random data set. Okay, so like, so it would learn irrespective of like whether it is completely random or like has some structure, right? Like, of course, if there's some structure in the data, the problem is easier, right? Like, so if there is no structure in the data, then you need much more capacity to fit the random function. Okay, so let's assume that the data is generated by some random process del X. Now, typically, your loss functions will take two things, right? Like, so one is the process which generated the data, okay, so which gives you the target that you care about, and also the parameters theta of the model. Okay, now these are the two quantities, right? Like, and let me just rewrite it in the next slide. So now there are two schools of thoughts on like which randomness like you consider or like where you put your randomness in this process. Okay, so what we have seen so far for the whole course is what people call frequentist approach. Okay, which basically treats del X as random. Okay, so we're going to treat the process that generated the data as random, and everything else is fixed. Okay, so given randomly generated data, like, so if you remember, all our expectations in the past were over X and Y, right? Like, so we assumed X is random, Y is random. Now, how do I learn a model like which has minimum expected risk, right? Like, so where the expectation is actually over the data distribution, right? So here we assume that the data distribution is random. We are sampling data from this random data distribution, and we are trying to fit a function to model X to Y, right? So this is the basis for everything we have seen so far, including the empirical risk minimization and statistical decision theory, right? So what we are going to do in today's class is a bit different from frequentist approach. So this is the Bayesian approach, where we are going to assume that theta is random. Okay, so we're going to assume theta is random. Data is fixed. So given this fixed data set, okay, we're going to assume that the parameters are random. We will estimate the best possible parameter given this data set. There is no like assumption about like data coming from a distribution. Like, so this is the data. Like, so like I give you 100 examples, and all you have is 100 examples. Now, how do you learn the best model that is possible, right? So that is the Bayesian approach. Okay. Now, some ML courses introduce Bayesian approach from the beginning. Like, for example, like if you read textbooks like Bishop, which is very Bayesian, like so they introduce Bayesian approaches from the beginning. Like, well, I chose to use it in the end. Like, this is just a different way of looking at things. Yeah. What? We'll come to that. So we will come to these questions like, is GDA Bayesian, or like is there anything else that we have done Bayesian? Like, after I introduce some basic Bayesian methods. Okay, so let's start with some simple algorithms. Okay, so before that, like I want to again talk about the parameter estimation problem in detail. Okay, so typically in any machine learning problem, there are two important things that we should consider. Okay, so the first question is, given some data X, okay, the goal is to estimate the value for a set of parameters theta that can best explain X. Okay, so this is called the estimation problem, which is basically, given the data, can I find the best possible parameters? Okay, now why do we find these parameters? To do the prediction, right? Like, so we want to learn these parameters and then do the actual prediction, which is the second problem. So which is to calculate the probability of new observation, let's say X hat, given previous observations. Okay, so what is the probability of X hat given previous, right? So this is the prediction problem. Okay, so I want to highlight that our ultimate goal is always prediction, right? Like, so like, why do we do parameter estimation? We are doing parameter estimation because we want to fit the data, the model that is going to help us make the prediction, right? So in some sense, the first problem, the estimation problem, is just the means for solving the second problem, which is what we care about. Is that clear? Okay, so now let's start with some simple examples. Okay, so like, we will do supervised learning, but before that, I want to start with unsupervised learning. Okay. So what unsupervised learning problems we have seen so far? Clustering. We have not seen clustering. When did we see clustering? KNN is still supervised learning, right? Yeah. So what unsupervised learning problems we have seen so far? No. Okay, now don't make me feel bad for asking this question. Like, so. Yeah.
Autoencoders and like Fisher's criteria.
Yeah, so autoencoder is an unsupervised method, right? Like, because there is no labels, like it's just the data. But is Fisher's criteria unsupervised? Don't you use class information? What else? We have seen a few. Yeah?
PCA too.
Sorry?
PCA.
PCA. So PCA is unsupervised. Like there is no Y. It's just X, right? What else? Have we seen any other unsupervised learning? Okay. I think that's it. So we have seen PCA, which is a dimensionality reduction method, right? And we have also seen autoencoder, which is another dimensionality reduction method, right? So in general, like the main unsupervised learning problem that we have seen so far is dimensionality reduction, right? So today we're going to look at another unsupervised learning problem. Okay, so this is called density estimation. Okay, so what is density estimation? So the idea is given some data set of x1, x2, xn. Okay, so I give you a data set of a bunch of x. Okay, so the goal is to learn the like a probabilistic model which tells you the probability of each data points. Okay, just learn the density function for this data, right? Now, can someone tell me where could we use this density model? If I learn a probability distribution for the data, so remember this is very different from learning probability of y given x. We are not learning probability of y given x. Okay, so we're just learning a good model for p of x. Okay, so if I have a good model for p of x, where can I use it? What kind of applications you could use it for? Yeah. Okay. Yeah. Anomaly detection, right? Like so, like one of the benefits of having p of x is if you have a new data point coming in, and the probability of that data point is very low with my density model, then it just means that this is some kind of an outlier from the data I have seen so far, right? So then maybe I can choose to not use my classifier, saying, oh, this is an outlier. The classifier is going to perform bad. So I will not use my classifier here, right? Like and fall back to a human decision maker, right? Like so, like one of the applications is outlier detection or anomaly detection. Okay. Anything else? So you had some.
Well, then you can sample, right? Create like synthetic data.
You could sample from this because P of X is in some sense a generative model, right? Like, so when you have access to the probability distribution of X, you could sample as many X from that as you want, right? Like, so you could do some sort of generation. So generate new samples. Okay, so what else can we do?
We're going to use wire for the defensibles.
Sorry?
Wires.
Oh, well, it depends on what you call a sample. So like if you think XY pair as a sample, yes, you need Y. Like, but if you just want to create a bunch of like think about training a density model with all the images that exist out there, and you just want to generate new images, right? So there's no class labels. Like a more solid example is like just train a model to fit all the human faces, and like you want to sample new faces, right? Any other applications that you could think of? Well, the other thing that you could do is you could also condition this density model on something and get some sort of conditional generating models. Okay, so like for example, like what was the probability of X given some prompt, right? So you could still estimate the probabilities, but conditioned on some prompt, right? So there are many interesting applications of like having a good density model, and this is also very close to the generative models, like the popular LLMs that we see nowadays, right? Like so they are in some sense trying to just fit P of X, right? Like at least the initial pre-training stage of LLMs is fitting P of X, where X is the entire web data, right? Like so, like can we model the distribution of all the text that exists in the world, right? Like so, like and get a really good probability model for that. So that is what most of the initial pre-training does. Is that clear? Okay. So now let's say I have some data X, data set X, which has a bunch of data points. Okay. We're going to make the usual IID assumption, which means the data is independent and identically distributed. Okay. So can someone tell me the implications of making this IID assumption? So like, what does it really mean? Like, so why should we make this assumption? Yeah.
Samples are independently drawn, and so they're, well, you have the independence from it, and you build it off of the solution.
So what would happen when samples are not identically distributed?
We couldn't make an assumption on the distribution.
Well, it's going to be harder to model, right? Like, so it's going to be very difficult to model things if they are not coming from the same distribution, right? Like, so the benefit of having everything coming from the same distribution is you can say, oh, I'm going to assume that this distribution is Gaussian, or I'm going to assume that this distribution is Bernoulli, right? Like, so this is possible because of the IIDs, right? Like, so, and what about the independent part? Like, so what would happen when samples are not independent? So how would it affect the learning? Yeah.
Like, let's say the formula, you want to, as soon as you want to see the probability of seeing two samples, there would be some cross terms that would appear in the computation.
Yeah, so typically when you do maximum likelihood, the reason why you are able to do products of I is equal to 1 to n, P of y given x, or P of x, right? Like this is because we make this an input. Okay. So in some sense, this is a very crucial assumption which almost all the machine learning algorithms, at least the algorithms that we have seen in this first course in machine learning, make, right? Like, so of course, there are modern algorithms which breaks these assumptions and designing methods that would work when IID assumption is violated is like one of the core research topics in machine learning. Okay. So for now, we're going to make the IID assumption, and typically, if your data is, let's say, real value, right? Like, so then we could assume that X comes from a Gaussian, right? So which means the parameters that we are estimating are mu and sigma square of the Gaussian, right? Now, given the data, the probability of theta given X is what we are interested in. And this can be written using the Bayes rule as P of X given theta, P of theta by P of, right? Where this is the posterior that we care about, and this is the likelihood, and P of theta is the prior, and this is the evidence. Is that clear? Okay. So first we are going to start with what we have already seen so far, which is the maximum likelihood estimation. Okay. So in maximum likelihood estimation, the loss or the objective is defined as basically the probability, maximizing the probability of X given theta, right? Like the likelihood. Like, so this is what logistic regression did, like, and a lot of other probabilistic method we have seen has done, right? Like, so given the data, you just try to maximize the probability of the data given theta, right? Like, so this can be written as product of x belonging to x, p of x given theta, and I'm able to write this as a product of individual data points because of the independence assumption, okay? And typically this product is going to be a very small multiplication of very small values. So we would consider the log likelihood, right? And theta for maximum likelihood estimation is defined as argmax of the log likelihood, right? Or in other words, argmax of summation x belonging to x log p of x given theta. Is that clear? Now this is the estimation part of MLE, right? Like, so the estimation part is just to learn the parameters. Now, once you learn the parameters, how are you going to use it to make prediction? So that is the prediction part, right? So for the prediction, the goal is to estimate the probability of new x given the previous data points, right? So this can be written as integral p of x given theta, p of theta given x d theta, right? So we are interested in p of x given the previous data, like, right? Like, so here you see how we are using the theta. So we first learn the theta from x. So that is p of theta given x, right? Then when you integrate the theta out of this equation, you're going to get p of x given x. Is that clear? So ideally, this is what you should be doing. So you should be integrating out the theta, right? Like, but as you can imagine, this is almost intractable because like there are infinitely many possible values of theta, and like so this is going to be really difficult to do. Yeah.
Why are we looking for a new x again?
No, the prediction problem is like what is the probability of the new x given everything you have seen so far?
Or like generate the data? Like I don't understand.
No, okay, so the estimation, okay, so the density estimation problem is to fit a probability distribution for x such that given a new x, the goal is to compute p of x. That's it, right? Like, so if we are interested in computing p of x dash, okay, given the data we have seen so far. Okay, well, that's just 1 second. So, well, we are talking. Think about what is the real problem here, right? Like, so the real problem is somebody gave you some data, and they're going to give you a new data point and ask what is the probability that this data belongs to this data set, right? So the parameter is just something that you decide in between, right? Like, so let's say you to answer this question, like you decided to come up with a model which fits the data. Then using the model, you're trying to predict p of x. So that's an intermediate estimation step, right? Like, so the real goal is always this, like just like how in any classification problem, the real goal, if you think about it, is what is the probability of like y hat given the new data point x hat and the data sets, right? So even though we often write what is the probability of y hat given set and the parameters, right? In a typical classifier, you learn some parameters theta, then given new x, you predict y, right? This is our solution method. The original problem is given some data set of x and y and a new x, can you predict y? There was
Can you go on the last slide?
yes.
Well, what is the estimation here?
We are estimating theta.
And what is the like triangle with the equal?
Oh, it's just a definition. So that just means that I'm defining
Okay.
it as p of x given theta. Okay, so here's this part. Yeah.
I can't see the transition.
Each term here.
Yeah, like in the segment, like just.
Well, we are interested in P of X dash given X, right? I'm writing this as P of X dash given the parameters, which we know how to compute given the model. Then what is the probability of the theta given the data point? So when you're essentially marginalizing theta here, so you will get P of X dash given X with that. Okay. Now, in maximum likelihood estimation, we are actually approximating this by saying, okay, so I'm going to approximate theta with theta ml, right? So this becomes P of X dash given theta ml times P of theta given X d theta, right? So what I'm trying to show here is maximum likelihood estimation is just an approximation. Okay, so we approximate the prediction question by saying, okay, I'm going to compute the parameters which maximizes the likelihood of the data. So that is theta ml, right? And I'm going to plug in that here in this equation. Now, the first term is independent of theta. I can take it out. So this becomes P of X hat given theta ml times integral P of theta given X d theta. Now, what is the value of this integral? 1, right? Like, so it's just integral theta P of theta. So this becomes P of X hat given theta m. Okay. So I'm just trying to formalize what we have done so far in this course, which is basically we wanted to solve this original prediction problem, right? And we took the simpler approach of just maximizing the log likelihood of the data and fit the model using that and use that model to make the prediction. Okay. Now, as you can see here, this cannot be the most optimal thing to do, right? Like, so the most optimal thing is somehow compute this integral. Like, if you can do that, then you have the best possible prediction, right? Because you're considering P of X given theta, P of theta given X, right? Like, so we are not doing that with MLE yet. Okay, so what we are going to do in today's lecture is to develop more, well, I don't want to call them more efficient, but like better methods than MLE, like map or full Bayesian approach, like which is going to be in theory better than MLE in performance. Okay, I'm saying in theory because these methods are also costlier sometimes. Here, yeah. Sorry, what?
You said that memory of all my values now, but I don't understand because I not predict actually the label. The X given the better size, given the this provides learning.
This is unsupervised. Okay, whatever I'm putting here is unsupervised learning. Like, but what I wrote here, like before to explain, right? Like, so you can write the supervised learning version of this. Like, so like where you're predicting y hat instead of x hat, right? So yeah.
How do we have access to theta ml? How do?
Well, that is what we estimate, right? Like, so theta ml is basically argmax of log likelihood. If you do gradient descent with your parameters, like so with log likelihood as your objective function, we are going to get it. Yeah.
Have we demonstrated that if we engage the spiral probability amongst all possible x, the result is 1? Oh, no, I realized my question is typical, sorry.
It's given x. Okay, so let's look at a simple example. Okay, this is going to be a running example for all the estimators. Okay, so we are going to look at coin tossing as an example. Okay, so let's say I toss a coin for n times. Okay, and the goal here is to model the distribution of coin tosses. Okay, so that I can predict the probability of head or probability of tail. Is that clear? Now, if my goal is to model coin tosses, like what could be a good probability distribution? Yeah, Bernoulli, right? Like so like we can make an assumption that this actually follows Bernoulli distribution. Okay, with let's say the parameter p. Okay. Now, for Bernoulli, the probability that C is equal to C, where C is 1 means head and C is equal to 0 means tail, is given by P power C 1 minus P power 1 minus. Okay. So this is just a compact notation for the probability, right? Like, so when C is 1, which is head, right? Like the probability of head is given by just P, right? When it is tail, the probability of tail is given by 1 minus P, because P represents the probability of head. Okay, so when it is tail, this becomes 1. This becomes 1 minus P power 1, so which is just 1 minus P. Is that clear? Okay, so now this is the likelihood for one toss, right? Now, when you have n tosses, the log likelihood is given by log product of I is equal to 1 to capital N, the probability that C is equal to Ci given P. Okay, so I can write this as summation over I is equal to 1 to capital N log P of C is equal to Ci given P. Right? So let me take this to the next line. Okay. So now some notations, like we have totally n trials, right? Let's consider n1 to be the number of heads in these n trials and n2 to be the number of n0 to be the number of tails in these n trials in such a way that n1 plus n0 is equal to capital E. Okay. So now I can split this summation into two parts, one for heads, one for tails, right? So I can write this as n1 times log Pc is equal to 1 given P plus n0 times log P C is equal to C0, sorry, C is equal to 0. Is that correct? So there are n1 heads. So for each of these n1 heads, the probability is given by log P. And there are n0 tails. For each of these n0 tails, the probability is given by 1 minus log of 1 minus P, right? That is what log of P is equal to P log P of C is equal to 0 given. Okay. So this can be written as n1 times log P plus n0 times log 1 minus P. Okay. Now I want to maximize this structure. So how do we do that? Like we can do dou L by dou P and set it to 0, right? You're going to get the maximum likelihood solution. So how to do this? Like, so you differentiate n1 log P, you get n1 by P plus, so it becomes minus n0 by 1 minus P is equal to 0. Right? So, well, maybe as a practice, can you solve this now, like, and tell me what is P? I will do it, but you okay, wait, let others do it. I'll give you a couple of minutes. Can you solve this and tell me what is P? I will take this to the next slide as well. You should try if you want practice for your final. Okay, do you all have the answer? What is P? Yeah.
Okay.
Yeah.
It's the number of N1s over
N1s over N. Does everyone get the same answer? So it's simple, right? Like, so it's like if I have to do the whole steps, this is 1 by P minus 1 is equal to N0 by N1. Okay. So 1 by P is equal to N0 plus N1 by, sorry, by N1. So P is actually N1 by capital M. Okay. Now, this is very intuitive, right? Like, so what does this mean? Like, so if you run the coin toss experiment 100 times and it was head for 40 out of 100, then the maximum likelihood estimation for P is 40 by 100. So the probability of head is just the sample frequency, like, so it's 0.4, right? Like if you had 40 head out of 100 runs, like it's 0.4. If you have 50 heads out of 1 runs, it's 0.5. Is that clear? So just as an example, let's say I ran the experiment 20 times and N1 was 12 and N0 was 8, then the maximum likelihood estimation for P is given by 12 by 20. Is that clear? Any questions so far? Okay, so now obviously there are issues with maximum likelihood estimation. So can someone tell me what kind of issues you would face in this coin toss experiment if you're just doing maximum likelihood estimation? So let's say I run this experiment 5 times. Yeah.
don't.
You might not think that this is possible. You know, it would happen.
So if you don't do enough tosses, like you might not get accurate estimate. Like the best example is I toss the coin once and I get a head. Okay, so what's the probability of head after that? You're doing maximum likelihood estimation. The P is given by 1 by 1. So the probability of the next toss being head is 100%, right? And let's say I repeat, well, in practice, when you repeat the coin toss twice, like you're not going to get head and tail, right? Like you might get head and head again, right? Like so, the second toss is heads. Now this is 2 by 2, it's still 100%, right? Like so, the third toss maybe tail, right? Like so, as you can imagine, like if you don't do enough coin tosses, like you are going to overfit, right? Like so, overfitting, as we have seen in all the previous methods, right? Like is happening. One of the main reasons for that is you're doing maximum likelihood. Okay, so when you do maximum likelihood, you're really trying to put all your energy to fit the data, right? And this is problematic if you have very small amount of data or there are abnormalities in the data which doesn't exist in the test set, etc. Right? Like so, this is when overfitting happens, right? Like so, now how do we avoid overfitting? Like now with this view, right? Like so, if you think about our solutions for overfitting, so one of the easiest solutions to add more data, right? Like so, when you add more data, you're really improving the estimation by making sure that the model is not just referring to the small amount of data, right? Then we also talked about regularization. So how does regularization fit the picture here? Like so, well, maybe let's take a 10-minute break, and then we are going to talk about better ways of estimating parameters. Okay, so we'll take a 10 minutes.